All right. Thank you, Kent. Appreciate that. We live in several different worlds, all of us. Most of us live in our head. Then we live in the space, and then we live in the music. So dumbing this down to what we're all interested in. Sometimes the music is just the tool in the toolbox that we use to test the things that live in our heads. Sometimes the music is the thing that lives in our heads, and the other things are the tools we use to more fully experience that sound, that field of tone or sound field, however it works to you. I'm going to make an assumption that you all live in the world of silicone or vacuum tubes or some variation of parts and pieces. That's another great world to live in. And when you assemble your parts and pieces, you are assembling in your head for a thing that you want your kit to do without much regard for the thing you're going to hook it to. It's going to hook onto a loudspeaker. Well, that's true, but what kind of a loudspeaker? And that's a worthwhile question, I think, relative to the kits that you're going to build. So if you're building a vacuum tube kit, and I'm sure you've had some seminars on the 300B or other classic single-ended triodes, direct heated tubes, or even early FET chips. These have kind of high output impedances, 2,000 ohms, 1,000 ohms. What do you do with a 1,000 ohm output device? If you want any power to be transferred from that device into the thing that then transfers that power into something that responds to your ears. Well, 1,000 ohm loudspeakers exist, and they match up interestingly to a 300B. They're pretty rare. There's some things you could build there, and that's another part of the hobby. But you've built an amp, and the amp looks like on paper that its maximum, its butter zone is for an 8 ohm speaker, which is pretty much a nice center point. Great. So what kind of an 8 ohm speaker? What does your amplifier see when you hook it up to an 8 ohm speaker? Does it see a resistor? Probably not. Even if you put something in between it, a transformer. Transformer is just a mirror. It transforms and it makes impedance ratios more friendly, but it still sees, if you put a dynamic loudspeaker on your amplifier, it's still going to see all this craziness. So what happens when an amplifier designer designs a loudspeaker? You get resistors. Is usually what happens. Resistors don't sound so great. Okay, that's another third part of this whole. What sounds good to this gentleman is probably not what sounds good to this gentleman. So the sensation of tone is unique to all of us, and there's no right way to skin that cat. And that cat, it lives in our head. We have what we have in our head, and it's because all of our ears are different. What we respond to is different. Our kits and how we build those kits are all different. The parts we chose. You're all going to want to build loudspeakers at some point because you want to optimize the box you built for the other box you're going to hook it to. And that's where I got my start. Well, one of the places I got my start. But you can typically, and the old timers the dead old timers, the guys that went way early, so 30s, 40s, 50s, they had a thing called theatrical perfection. It's a term I've tried to ignite, and hopefully this group will take the theatrical perfection ideal conditions and move it forward. That's when you have a big barn to work with. This, the Triode Mafia, Herb Reichert, and some of those crazy guys, the Silbatone guys. They play in the world of theatrical perfection. We don't. We play in the world of, it has to fit in my living room, and my wife can't kick me out of the house for having it in there. So we're going to be building dynamic loudspeakers that have a reaction, and you should consider this relationship with your amplifiers that you built. And I'm in the crowd, so far I probably haven't said anything all that interesting, and I apologize a little bit, but I think it's a worthwhile conversation piece to talk about how we think about our device, and how that informs our choices, and then how that informs our sensation to it, and the music we choose, and how that all interplays. Because if I want to play So in my shop, I've got a guy who's really got me into noise and doom metal and really complex music that is very wide bandwidth. And a term that you guys may or may not be familiar with is full bandwidth is a Z-weighted bandwidth, which is everything has equal weighting from the deepest bass to the highest treble. And to do doom metal right, which is basically shoegaze material dropped several octaves and two great big huge guys with long hair playing crazy shit out of their big bass rig that's, you know, taller than they are. That requires Z weighting in your amplifier. It's highly stressful for the amplifier, highly stressful for the loudspeaker. The best way that sounds good is if that power transfer happens, if all the bandwidth is equally represented and it happens in the same time. So impulse responses look good. If those things don't really line up, doom metal just sounds like the shit that you think it might sound like. But it doesn't sound like shit when it's done right. And the way to find out if it's done right is you go to a doom metal show and you listen to the guys with the instruments and they play the thing, and you know you're at least getting some proximity to what that sounds like, and that's in your head. And you get to carry that with you. So when you're designing loudspeakers. So back to the designing of loudspeakers. They have to fit in your in your room, and you're building a straight up kit based on an 8 ohm load. And let's say your kit only puts out 2 watts. 2 electrical watts is a whole lot of acoustic power if you had 100% power transfer. I mean, it's a rock concert in your living room. That never happens because we throw 99% of what we create in our little kits as heat, and it doesn't come out as sound pressure. So, some interesting designs, and I'm guessing most of you guys are low power guys, because that's both easy and fun, and it has a sound that I love. But you take that low power kit box that you did, or something that you created, and you put it on something like an old Western electric horn array, it sounds pretty fantastic. I mean, maybe some of the best sound there is. But yet, again, it only fits in a barn. It only fits in a barn. So your wife, everybody's upset. Everybody's upset about this, including you, because it doesn't fit through your door, even if you could get it in your house. So, and you don't want to go buy the barn. So how do you get that power transfer? How do you get the efficiency in your house? Well, there's a lot of drivers that can help you do that, but those drivers are also this reactive, because they don't have a horn on them to convert this dynamic load into a resistive load. So now you're one of the cool things about horns is that they do present a resistive load. They are the resistor that you all idealize when you're doing your designs. And I love horns. They don't fit in my house. Not yet. Someday.
What about line array?
Line arrays are super interesting too, right? And we can talk about that. And maybe now's a good time, because I didn't really obviously prepare a lecture. I thought we would do more question and answer stuff. And I'm making myself available after this until till supper time. And so if I can help in any way, or if we can learn together, but the cool thing is this whole group is trying stuff. You're soldering parts together, and you're cutting things up, and you're measuring, and then you're listening, and you're trying again, and eventually you're going to find that you're going to get the goosebumps you're looking for. I love that. That's how I got into this stuff. One of the things that got me into this is because I had dirty hands. You all have dirty hands, and with dirty hands come the dirty minds. And I think it's beautiful, and to be open to JFETs. Well, I have a thing for FETs, but also, well, I have a FET. Let's see how it runs. What if I do this Class A FET and I don't mean to talk about amps, I'm supposed to be talking. But anyway, power transfer is something that I care a lot about. So when I design a loudspeaker, I think of the amplifier I'm going to put it on. And I try to get the power transfer as one of there's lots of facets. This is all simple stuff, but there's a lot of things to think about when you're doing this. And the more of the facets you can visualize in your head world, the better the outcome in the real world will be. So, so line arrays, and I'm sorry, your name?
Anatoly.
Nikolai.
Anatoly.
Right. These are your speakers?
Yeah.
Great. All right. Would you like to talk about them?
Sure.
Yeah, please.
Oh.
Yeah, right now. Yeah, because this is a great example of things you can do and why they, I mean, you don't have to. I'll talk about them. And you can say yes or no, right? How about that? So one thing that we didn't talk about in this is, so wavefronts are important. So that's the real world is wavefronts. And so if you want to think about it, so you all deal in the electromagnetic world, which is a field. And this sound field, it's not quite the same, but it's a good way to consider the two things, where it's analogies that do kind of work. So how you hear something, it interplays with the sound field, interplays with the whole of the field, the whole of the space. And a line array is an interesting way of manipulating your wavefront. So the wavefront has nothing to do with this 2D space of the amplifier loudspeaker relationship becomes a 3D space as soon as you go into the world of sound. So if you choose to build a line array, you need to know why you're building a line array. It's not because I can make a 64 ohm speaker by wiring everything in series. That's a thing, and it's a worthwhile thing. But you could also build a dodecahedron that is got a bunch of little drivers all over and get 64 or 128 ohms, and we're rounding to these nice numbers, but 200 ohm, whatever, close enough. Butter zone. I love butter zones. Exacts, they don't work for me. Close enough is enough. So the line array, it produces a cylindrical wavefront. If it doesn't have to, it can. You can have a Diapolito line array where we're talking about wavelength relationships, and that's a different way in which to shape your 3D space and how you hear something. I like to use line arrays as a full bandwidth line array. All you guys have probably had, and girls? Sad, not one girl. Work on that. In the back, right? No, maybe. All right, anyway, so full, and like it matters. But what I'm saying is more diversity is a really healthy thing. All right, so line array, all full range. Say a Stax planar speaker. They call them planar because they, in a certain wavelength relationship to the device, it produces a planar wavefront. But actually, it's a kind of a misnomer because a planar wavefront, it would have to be it wouldn't be a stick. The Stax would be a round dome, and it would only be planar relative to its wavelength. So it's not really putting out planar waves. It's still putting out, but this is putting out a cylindrical wavefront. And because the tweeters are spaced off, much greater the distance of the wavelength that they are playing, they are angled to try to distribute that energy evenly among this room. If you are playing to the sweet spot, however, we've all been to live shows, and the new shows ever since 80s and after suck for sound at shows, mostly. I mean, unless the guys have their gear with them, go to doom metal shows, because then you're hearing what the artist is hearing, and it's really a pleasant experience, and the people are wonderful. Okay, so on this, I actually got sidetracked pretty good there.
Cylindrical wave launch.
Yeah. If you want it cylindrical and you want it to be full bandwidth, it's a very long array if you want bass waves that are also cylindrical. If you go to a show and it's at an amphitheater, for example, and they have a bunch of bass bins across the front of the stage, and then they have their big line array, which is a J-shaped J array, you have a cylindrical wavefront for the majority of the bandwidth that we're sensitive to, but then you have this big bass array. And since the bass waves are 10 feet, 20 feet, 40 feet long, who cares if it's not stereo? Who cares if it's not the same polar response as we measure? Well, it matters. It's one of the reasons why big festivals sound like shit, is because the wavefronts are radically different between bandwidths or the decades or the octaves within the bandwidth. So when you're designing, it's easiest to start with the ideal isotropic source, or at least a point source, so that your wavefront is conical. So it produces a point, and all of your. But it's impossible. It's a nice ideal, but it's highly improbable any of us can make that happen without a great deal of expense. And keeping it simple is a great way to find the tone and the sound. So single drivers, I'm a fan of single drivers. Line arrays, these are basically, I mean, it's a simple two-way driver in a line array for maybe you have an impedance position that you want to arrive. I want to have 128 ohms, or I want to have 48 ohm loudspeaker for this, because it's going to work with this weird esoteric germanium chip I found on the internet. And I want to build an amp around this wacko germanium chip, which is fun, I agree. So you need 48 ohms, but if you know that you also have the wavefront, the three-dimensional component of it to consider, it will help you realize the real sound that exists outside of your head. Yeah, so that's a simple explanation for a line array. There was a lot of talk in that. Line arrays present a conical wavefront. And since this is a sealed system, or even if it were a ported system, it presents it with a very vector directional propagation. It's not truly cylindrical. It's cylindrical within a certain polar, vertical and horizontal plane. But it does produce, for the most part, this is producing in 80% of the sound coming out of my valve, which is coming out of these speakers. It is a conical wavefront. So it's a solution to a problem if you know the problem. Gentleman in the back.
I've got several questions. Somebody else wants to ask one of them. Just chime in. First of all, I want to ask you a question.
Your name first. Milo. I mean, if you'd like. Milo. Sure. Nice to meet you.
Those appear to be like 6-inch drivers.
Right.
And is that a dual cone? My eyes aren't quite big.
Nope, single cone, single voice coil, but with a tweeter mounted on the front with its own voice coil.
Oh, okay. So it's actually a coax then.
Yeah, coax.
Okay.
Right.
I can't tell that.
Right.
But anyway, as far as the 6-inch speakers, at what frequency do you get cancellation? And when you stack them like that, a certain frequency that will happen. What frequency would this setup?
So there's some simple math to tell you about your polar response and how that wave propagation is going to happen, and also when the loudspeaker, we call it breakup, that's the first modal condition of the cone. Those are some very interesting questions, and those are explored really thoroughly in the book that you all should own, which is Harry Olson's Physics and Music. Is it called Physics and Music now? Harry Olson, he has one book. Buy that book. And it lists it out without a lot of heavy math. In fact, the math is really simple in Harry's book. And he's the pioneer of the dynamic driver. But the modal, so comb filter or cancellation, destructive interference, yes, that's something we all live with because there is no such thing as a point source. It doesn't exist. If it did, well, it wouldn't. It can't. So you can have the idea of a point source and you can stretch to it, but you have to delineate it. You have to put some triggers on that to keep it from going infinitely small. Yeah. The what?
Within limited bands, yes.
Yeah, with a limited frequency.
Yeah, you can strive to it. You can never get there, but just apply a little calculus on the problem to keep your head from imploding, because it will. You can't. Again, butter zones. If you try for an absolute, you will go down the wrong path, for sure. I think that's my experience. Yeah, but so the cone will break up. So the cone membrane has a propagation velocity. There is no such thing as pure pistonic motion relative to a large bandwidth. There's always going to be a deviation between what happens at the voice coil to membrane contact and what is happening at the contact to the surround. Always. Ionic drives are a little different there, and so are membranes that are driven by an electrostatic panel. But still, there's propagation velocities in all of these. But most of us are going to build dynamic speakers because you can order those things from, US Speaker or Parts Express or Matasound, and we get our little kit of parts. And I would encourage you, if you're not building speakers, to look at Matasound and some of these parts places and try some stuff. Just start trying some stuff, and then trust your response to the thing that you build. There's no perfect, there's no perfect amp. They don't exist. There's no perfect power supply, let alone a perfect amplifier. Did that answer enough of the questions? Because really, this is a deep question.
Yeah, I was wondering if the fellow that built them had tested them and would actually know what frequency you get for cancellations, not just putting it into a formula, which has lots of variables.
I'm sure he has measured these. But you could do some quick calculations too. So we have 8 inches, 7 inches between tweeters. Propagation of sound in air, and temperature is your big variable there. It's not a constant, 1,128 feet per second. It exists at a few points around us, but really, 1,000 feet per second is a close enough butter zone measurement so that you can do these quick calculations. And at quarter wavelengths, that's the magic, quarter, half, three-quarter, full wavelengths is that's when those the wave function, the wave mechanics really reveal themselves. That's when you're getting destructive and constructive interferences. So if at 7 inches, let's see, half a foot, 2,000 at 2,000 hertz, we're going to have some radical beaming, lobing issues. But how radical? Well, we have a distribution of these nodal points. And so we have quite a bit of overlap in these null points, so that those null points become minimized because we have 8 tweeters on there. So the more drivers you have, the reduced sensitivities you have to nulls and also the anti-null or anti-modal points.
There is one more point.
Yeah, so, go ahead.
Usual misunderstanding is that you take differences between these tweeters and calculate how many wavelengths you have here. It's wrong, because sound propagates not from here to here, but from here to your ear. So there is a triangle. So you have to calculate difference in distances from your ear to this tweeter and to this tweeter. And the further you are from tweeters, the less this comp effect you hear. Of course, if you can right in front of speaker and try to hear frequency response, you hear home filter effect. But when you go further, you don't hear.
Yeah, that is true. So the further away you are from the source, the more point source it becomes, or more point source like. Yes.
I have 2 questions, and they're a little more general. Who are you designing for, and what is their idealized listening environment?
I design for myself, and I hope people like what I design. Sometimes I'll design for other people if they bring me commission, or if they bring me, my company is Zoo Audio. We do have a plethora of scabby, weird products because, again, I have an amp I want to hook up. I want a 16 ohm speaker and I want it to do this thing. So I design a speaker for that thing. And so, but yes, our simplest product, Omen, we have a product called Omen. It behaves mostly like a single point source, single driver speaker. It's a 10-inch frame with a super tweeter or a tweeter that comes in at 12K. Acoustically, there is a handoff between the full range driver and the tweeter, but 12K. And that is, for me, a good example of what I design. So it might, but again, I like my hands dirty, so I design a lot of different stuff. But it's almost always for myself, and then commercially, I just hope you like it. But I don't expect it. Okay, is that a weird answer?
Sure. What's the environment?
Homes, mostly homes, unless it's a commission where I'm like, oh, okay, I know the full parameters. I know what the guy wants. I know the amplifiers. I know the space. I know his targets. And that's another thing. Most people I talk to on the phone have a vague idea of what their targets are. And you can help yourselves by thinking more about what you want to arrive at sonically or musically. Like, oh, I want Fleetwood Mac to sound this way in my house. My house looks like this. Then designing a speaker to do those things within the context of my amplifier is a high likelihood of success. But if you say, I want it to sound good, that means nothing to me as a friend that's trying to help you get sound, a good sound, a tone, right? So, but yes, the more you understand your parameters or the environment in which it will play, the closer you will get to your truth. It's subjective. So I use the word truth in a strange way there. Please.
What is the difference between a waveguide and a horn?
A waveguide, they're interchangeable a lot of times. A waveguide definitely shapes the wavefront, and a horn doesn't necessarily shape a wavefront. So if you have a waveguide that is also a horn, so it's function.
Is it the depth that makes the difference?
Yes, well, okay. Then you get into particle velocities and phases, and also, yeah, and yeah.
Doctors have stethoscopes that are waveguide.
Yeah, that is a form of a waveguide too. So that's a transmission line style waveguide, in which, like in the RF world, the antenna is the waveguide. So in RF, you guys are, playing in the RF realm. A 2-to-1 box, an aluminum box, is going to allow you to transfer radio frequency through that with almost no impedance loss, or without any loss, and the bandwidths are crazy. So in acoustics, you can do the same thing if you need to transfer a sound from A to B. But this is kind of complex acoustics. It really doesn't make much difference to us as trying to play music, but some of that math does totally play into how you design horns. And so like a JBL, Keel?
Yeah, the Keel, but the classic, if we want to talk commercial product in horns that people might be familiar with, you go back and you look at the old Altec 500 hertz horns, the 511s, any of those, the derivatives of that, the TAD horns, they tend to have a sweet spot when you're listening to them in the near field being less than, say, 30 feet, that it's a very, very small sweet spot. It's like having the head in the vice type listening response. And you brought up JBL. I had the pleasure of being at the JBL factory when they were just finishing up the design on a studio speaker that they have called the M2. And the M2 uses a very advanced waveguide for the mid-range and tweeter. And so you walk in, and it's a room about this size, and here's this pair of speakers that are literally sitting in the two corners. And you walk in, and the sound field, the spaciousness of the sound field as you walked in the door was phenomenal. But the sound field did not change no matter where you were in that room, even when you were between the speakers and behind the face of the speakers. They had calculated the power response. In other words,
Constant power up.
right, constant power output, exactly. Spatially, that no matter where you were in the room, the spatial characteristics and the tonal characteristics kept that same relative balance. And that to me is kind of the difference between waveform and a simple horn that's an impedance transmission device.
So they were using the walls to do that.
No,
They were-
no. I'm sorry. A little.
Well, yes, a little, but of course. They were playing to the acoustics of the space they were in. So they knew their target audience and they knew their target space.
Right, they weren't worried about reflections because they were using reflections.
They were
It was
using the
direct
reflection.
right.
Exactly.
We'll definitely. So I've got. We definitely don't want to tread on Nelson's time. So we've got 10 minutes. Just okay. So horns. Treat a horn as different than a waveguide, and I would think of them differently. Even though all the things, I'm making speculation here, that we think of horn has waveguide properties built into that horn design. Whether it was by design or not, it's still wave front and wave development and distribution of energy is considered or is a result of the horns. Why do we have horns? Well, because they're called drivers because they drive a horn. You have to get, so power transfer. If you have 2 acoustic watts and you out of 2 electric watts, for one, that's never going to happen. But maybe you can get 1 acoustic watt out of 2 electric watts. And if so, again, the doom metal show sounds like a doom metal show in your house because that's a lot of acoustic power. 1 acoustic watt in your house is a lot. Horns are necessary to get that. It's essential because a direct radiator, the moving mass or the mass of the membrane and the air density, the density of the cone, the density of the air are radically different. So the same reason why you can't get a JFET with an output impedance of 0.1 ohm to play into a loudspeaker with any good efficiency is because generalizations are tough. But it's hard to get the power relationship between your devices. And the closer those are, the more power is transferred. But then it also, we fail to think, oh, maybe it needs damping. Maybe we need electrical damping from our amplifier, so we consider output impedance of our amplifier. Well, maybe the loudspeaker was designed in such a way that it's critically damp, and electrical damping means nothing whatsoever to the amplifier, or to the loudspeaker, or to you as a listener, because it's not going to change your sound. If you have high output impedance from the amp, or low if the loudspeaker is critically damped. Does a critically damped loudspeaker exist? Not uniformly throughout the bandwidth. In target areas, sure, you can do it, but not through a decade or a large bandwidth product. So you have a driver, and you want that driver to see a resistive load. You don't want it to see a reactive load. You don't want it to unload itself by having the particle phase go negative. The driver always wants to see a pressure against it, so truly resistive. So horns are how we accomplish that. Well, but then, yeah, so quarter wave is the end of life for a practical use for horn because your particle phase unloads the driver at that distance. So it no longer is resistive, it's reactive. So quarter wavelength is the minimum threshold for any horn or tube or straight waveguide. You know, a tube is a waveguide of sorts, right? Okay, so, and then the other function is, okay, I understand what I want to do to the driver and how I want to damp its electrical acoustic response, or how I want to tame reactivity, or how I want to exacerbate certain reactivity. At that point, that's a known, and then you can apply, well, what waveform do I want to generate? I want to design an amphitheater that has uniform distribution of energy and energy phase relationships throughout this 180-degree bowl. How do I do that? Well, everything's got to be able to produce the same type of wave. And since point sources are impossible, it's a problem to be solved. And same is true in your home. If you want to play 20 hertz, oh, one other thing, and then 2 questions and we got 5 minutes. Okay, here's a wives' tale that drives me crazy. Well, there's lots. 1, you have to have Harry Rosenberg. Anybody remember Harry Rosenberg? Great guy, but yeah, he's moved beyond. I mean, he could be here. He was crazy, so he might be hanging out with us. You know. What's that?
We're outside wearing a kilt.
Yeah, for sure. Yeah, and teasing all of us with hair.
Yeah.
So he would say sometimes, you know, hey, I need a big enough room to hear the compressive quality of a 20 hertz waveform. All right? So we extrapolate that as, well, we need a large enough building, a barn, because he probably had one, I'm not sure, so that I can hear 20 hertz. Well, you can hear 20 hertz with a headphone or with in-canal monitors. So waves, acoustics are all pressure waves. There are no shear waves in this fluid that we're breathing in and listening to. There's only compressive wavefronts. And so you can have 20 hertz sensation with earphones or in canal, or with some little teeny 4-inch driver that you bought off, I don't know, Parts Express or, Mauser or wherever, and you can make this do the thing. Just, if knowing that you want the thing to happen is a big part of the battle. But don't put limits on yourself. If you don't understand something, pretend you do and move forward with it. Because trial and error and elbow grease go a whole long way. And if you blow it up, your pieces were cheap, except for those Lundahl transformers. They were kind of expensive. Or maybe, those germanium chips, you're going to be kind of upset at yourself for blowing those up because there's like 20 left. But otherwise, it's cheap parts. All right.
So first of all, I want to say if you want to experiment with horns, Nelson Pass has donated the smaller of the 2 sets of horns that were in his storage locker. They're 3 foot around, 3 foot long, have about a 3-inch throat on them. They'll be in the raffle.
Excellent.
Secondly, you mentioned that you're designing speakers quite nicely with amplifiers. What do you expect from an amplifier? What amplifiers don't work well with your speakers? What work really well?
All right, so I don't have expectations of amplifiers. I look at amplifiers as dates. So how does that date play in my date world? So like the first watt stuff that maybe you guys are familiar with, somebody might call me on the phone, hey, which first watt amp do I want to buy? Well, they're one-trick ponies. And I know that's overly simplified, but a lot of the 80s music that we all love was coke-fueled and sounds really terrible in the presence region. It's all pumped to presence heaven. And so it sounds good and impressive until you listen to it on your systems that sound good, and you're like, oh man, I can't listen to this. My ears are bleeding. So then you pull out the first watt F6, which has a nice, lazy interstage transformer on the preamp, the line level side, and that rounds things off really nice. It gives it a certain tone. So I might design a speaker either to solve my problem, listen to the 80s music, I need to kill the presence. Well, there's other ways to kill the presence. You could buy an old Rupert Neve designed board that had some silk, and you can dial that in with some kind of a distortionary feature. Or you can build a loudspeaker that might have a notch filter, or build a filter of some sort. Or you can buy an amplifier that has those patterns in it. So there's a lot of ways to skin a cat, and that's how I approach problems. It's an interesting feature. A problem is a feature to enjoy. It's just like a jump face on a motocross track, or if you're doing battle with your buddy on the ski or whatever it is. It's a problem to be solved and enjoyed. So look forward to problems like this.
Hands dirty.
Yeah, dirty hands, dirty minds. Yeah.
Do you have your speakers built?
They're in the car. Yeah, we can dig them out.
By the way, I have a couple of amplifiers with switchable output resistance from big to negative, if you want to try.
Yeah, well, and so one of the things so this is my first time here, and by the way, I think this is really a cool event. So really, congratulations to the founders of this thing. I don't know you guys, this is super interesting. Some people I've overheard say this saved for me, this thing, not for me specifically, this saved my interest in hi-fi, is this Burning Amp Festival. And I love this stuff. I love the music, I love the kit, I love the speakers. I sometimes love the people. It's really cool that this is happening. So really, congratulations to all you guys. I want to design some DIY speakers. I overdo it in almost everything I take on. So I overdo it in a bad way. That's not a compliment to myself. That was the dig, really. So if you guys want to say, hey, look, I would like to build a kit. I don't want to design a speaker. I want to build a kit. Tell me what you want. I would love to get that kind of input. And there was one other question. Yeah.
Yeah. Can you speak to both directional radiation characteristics and ways to mitigate phase shift and group delay and low frequency response and speaker positioning techniques that you find favorable?
All right. So group delay. isn't a difficult thing, but it makes some assumptions. So it makes us some assumptions that
Because you're talking about extreme music, I'm talking about a tool. Loudspeaker is a tool for working on analytically extreme wideband.
Yeah. So if you want to design, there are so I believe efficiency and the lack of is a form of distortion. That, in my head, it's not something we measure, sure, but we all discount. Oh, we'll just pump more power into this loudspeaker. But again, the more the loudspeaker cone moves, the more harmonic distortion it's producing. It's a logarithmic analog, so it's a meter. But so if you're using it as a tool, like are you pro sound guy, maybe,
Yeah.
right? So you want to hear what you hear. You want to know what's in the box.
Yeah, what's on the file.
Yeah, right. And when I say in the box, it's jargon for what's happening inside either my desk or my computer or the software. So to do that, you want a speaker that has the minimum amount of group delay. So you want everything in time, so you have minimum amount of this phase interaction in bandwidth. Typically, but also this is a complicated thing, and so you have close field monitors, mid field monitors, far field monitors. You have cans sitting there on your desk, and these are all different tools to help you. If you're designing music or sounds, to help you figure out what is going on in this virtual world of your box. The best monitor would be a point source with perfect impulse response, with full bandwidth, and in my world, up here, is with perfect power transfer, so I could use my 1 watt amp and give me 1 acoustic watt, which will never happen, but it's a fun ideal to have. It's complicated. I'm happy to talk to you about it. Okay, so I think if...
105.
Thank you very much. Thank you.